Okay, so we're trying to describe the movement of water in soils. And so we've come up with this wonderful, I suppose Darcy came up with this wonderful equation, which said that the Darcy flux is going to be equal to the conductivity times the gradient in total potential. And I have a minus sign there. Okay. And so this is Darcy's law. And everything is fine. Let's identify some of these things. What is Q? Well, Q has a magnitude and a direction. Okay, so it's a vector. Okay? The gradient in potential also is a vector. It has a magnitude and a direction. And our friend K then is a scalar. So we say, aha, this is all very good. We have a vector on this side of the equation, a vector on that side, multiplied by a scalar. All of our terms work out. But there's a problem with that. What if I have a soil that at the microscopic level is layered? And this is actually very common when we have like a riverine deposit or a deposit at the bottom of a lake. Most systems in the world are actually built up of layers of soils. Now what we can see is that the resistance to movement of water across the layers is generally higher than the resistance with the layers. So how do we describe that? What we essentially have is a K in the vertical direction and a K in the horizontal direction. And so we have this directionality in conductivity. And it turns out what we have to do is we have to get rid of description of K as a scalar and represent it as a tensor. And so what that means is we'll have 9 values in general of conductivity. There'll be the effective conductivity in the x direction due to a gradient in the x direction, the conductivity in the x direction due to a gradient in the y direction, etc. And, of course, for the z and kzz. Now we have all the information about the directionality of, if there were a gradient in the x direction, how much permeability would there be in that same direction? Now, this is a very general way to express all the different possibilities of water movement due to gradients. But if we align our coordinate system with the layers, then all of what are called the off-diagonal terms become 0. So in other words, here I've drawn where my axis system is oriented with the layering of the soil. Had the axis system skewed with respect to these layers, I would have to maintain the cross terms. But here, if I align x and y exactly with the layering, then I don't have to retain those terms. Typically, the next thing we do is we say, aha, well, that's all fine, but actually the k in one horizontal direction is going to be the same as the k in the other horizontal direction. So we'll say ky equals kx. And so what we've now got in this system is we had kxyz, and now we're going to represent this as a k in the longitudinal direction and the k in the vertical direction. So we'll literally just boil it down to 2 terms, one to describe the conductivity perpendicular to the layers, and one with the layers, be it in the axis of the board or in the axis here, taking them to be the same. And so we have two conductivities that we use to represent the flow, the resistance to flow going with the layering or perpendicular to layering. And so when we look at Darcy's law, we often report the K as a scalar of particular value, but typically the horizontal permeability will be about 10 times the vertical permeability in a layered soil. So there's a little bit of the nuances of Darcy's law in layered systems.